We can inspect every weight in a language model. We can record every activation and replay every operation from the prompt to the answer. Yet this complete numerical trace does not tell us which higher-level computation the model learned. Mechanistic interpretability is the attempt to recover that computation, not merely to find an interesting pattern inside it. A strong mechanistic explanation names the internal variables, specifies the operations performed on them, shows how those operations compose, and predicts what will change under intervention. It also states where the explanation works, what it leaves unexplained, and whether a different explanation could pass the same tests. That is a much stronger target than making an activation human-readable. Our previous video, Beyond Pattern Completion, introduced the transformer. Here we need one level more detail. Each token carries a residual vector through the model. An attention head reads from earlier token positions and writes a new vector into that shared stream. A multilayer perceptron reads the updated stream and writes another vector. Thousands of these additions accumulate before the final state is converted into probabilities over the next token. Methods in mechanistic interpretability answer different questions. Does a component respond? Can an external tool decode information from it? Does changing it alter the output? Can a small set preserve the behavior? Do those parts form an organized algorithm? Is that algorithm distinguished from alternatives? And how much of the behavior does it cover? Calling every rung a mechanism hides the central scientific problem. Start with attention. For each destination token, a head compares its query with the keys at possible source positions. Those comparisons become normalized reading weights. The head then takes a weighted mixture of value vectors, transforms that mixture, and adds the result back at the destination. The attention pattern, therefore, describes where the head reads. The value and output transformations determine what it writes. This distinction is why an attention he-map is not an explanation of the answer. A bright connection can carry information that later cancels out, while a smaller connection can carry a decisive direction. The same visual pattern can write different content in different heads. Attention maps are excellent observations about routing, but the causal role depends on the information moved and how downstream computation uses it. Logit attribution asks a more output-directed question. Take the vector written by one component and pass it through the model's final readout. We can then see which candidate tokens that vector directly favors or suppresses. This isolates a linear contribution to the current answer. It does not reveal the nonlinear process that produced the vector or the later components that may amplify, cancel, or repurpose it. A probe attaches a new classifier to an internal activation. If the probe can recover syntax, sentiment, a board state, or a factual property, then that information is available in the representation. But the probe is doing additional computation. The original model may never read the same direction or use the decoded variable. Decodability establishes accessible information. It does not establish the model's own causal variable. Activation patching moves from observation to intervention. Run a clean prompt that gives one answer and a matched corrupted prompt that gives another. Save the internal state at every layer and token position. Then transplant one clean state into the corrupted run and measure whether the clean behavior returns. By scanning many locations, we obtain a map of where that particular intervention can control the chosen output metric. The reverse transplant asks a different question. Putting a corrupted state into the clean run tests whether the original state was needed to preserve the behavior. Clean into corrupted is a sufficiency-like test. Can this state restore the result? Corrupted into clean is a necessity-like test. Does damaging the state remove the result? Neither direction, by itself, explains how that state was computed or how it is normally used downstream. A patching result is inseparable from its experimental design. The prompt distribution determines which cases are averaged. The corruption determines what contrast is introduced. The replacement may be another example, a mean, zero, or noise. The metric may track one logit, a probability difference, or task accuracy. Change these choices and the localization map can change because we have changed the causal question. Interventions can also reorganize the computation. Subspace patching has changed an answer by waking a dormant parallel route that the normal model was not using. Ablation can produce the opposite effect. Downstream components increase their contribution and compensate for the removed part, the Hydra effect. In both cases, the modified network is not simply a transparent window onto the untouched forward pass. Patching and ablation are indispensable. Their secure conclusion is narrower than the word mechanism suggests. Under this prompt distribution, replacement rule, and metric, changing this internal state changes the behavior. To infer the natural variable or normal route, we also need evidence that the intervention stayed meaningful, did not manufacture an alternative path, and produced the predicted downstream changes. Circuit analysis tries to connect influential locations into an organized computation. Researchers select heads, multilayer perceptrons, features, or edges, replace the rest of the model with a baseline, and ask whether the selected subgraph preserves the task behavior. A good circuit should be faithful, should include the important alternatives, and should be small enough that the information transformations can actually be understood. Induction heads remain a genuine success case. In a small attention-only transformer, an earlier head can make the previous token available. A later head finds an earlier occurrence of the current token, reads what followed it, and copies that continuation forward. The weight structure, attention pattern, information moved, and behavioral prediction agree. This explains a precise copying algorithm, not all forms of in-context learning. The indirect object identification circuit in GPT-2 Small is a deeper example. In a sentence where John gives something to Mary, several classes of heads move candidate names, identify the repeated subject, suppress John, and increase the probability of Mary. The study tested faithfulness, completeness, and minimality, and reported unresolved contributions. It is detailed partial reverse engineering on a carefully bounded prompt family. The circuit's faithfulness score is not an intrinsic property. It is measured after everything outside the circuit has been zeroed, averaged, resampled, or otherwise replaced. Recent evaluations show that the same candidate subgraph can receive very different scores under these choices. The experiment is testing whether the circuit works inside a particular modified model, not whether it is the unique organization used by the original model. Redundancy makes circuit recovery non-unique. Two routes may each be sufficient, so different discovery runs select different subgraphs. Prompt changes can recruit new edges or alter the contribution of known heads. The stable object may be an equivalence class of computations rather than one canonical graph. A circuit must therefore be indexed by its prompt distribution, granularity, search procedure, and ablation baseline. At larger scales, localization has advanced faster than understanding. In a 70 billion parameter chinchilla model, researchers isolated a small set of components involved in multiple choice answers. But the proposed semantics generalized only partially when answer labels were randomized. Current circuit methods can often find where output-relevant influence concentrates. Recovering a stable algorithm across contexts remains much harder. Sparse feature methods begin from a coordinate problem. Individual neurons are often polysemantic, responding to unrelated patterns, while one useful concept may be distributed across many neurons. Under superposition, the model packs more features into a representation than there are clean orthogonal axes. Instead of treating neurons as the elementary units, we can train an auxiliary model to search for a sparser basis. A sparse autoencoder reads one dense activation and expands it into a much larger bank of candidate features. A selection rule keeps only a few active. The decoder then adds their learned directions together to reconstruct the original activation. Training rewards accurate reconstruction while penalizing the use of too many features. The result is a new sparse coordinate system placed on top of the original model. That coordinate system is extremely useful as an interface. We can search top activating examples, attach tentative labels, compare feature activity across datasets, and amplify or suppress a feature to generate causal hypotheses. Features associated with code, refusal, places, or the Golden Gate Bridge make a vast activation space navigable. This is real progress in measurement and control. But reconstruction does not identify the model's own variables. Different dictionaries can rebuild nearly the same activations while splitting one process into several features, absorbing only common instances, or mixing several causes. Standard autoencoders also assume that one feature corresponds to one direction. New work argues that genuinely multidimensional features can make that assumption actively favor feature splitting. The learned basis is not fully stable across training runs. Large sparse dictionaries trained on the same activations with different seeds can recover substantially different individual features. The newest evidence adds an important nuance. Unstable features may occupy reproducible low-dimensional subspaces. In some cases, the scientifically stable object may be a region of representation space, while the named axes inside it remain non-identifiable. Baselines expose the central weakness in current evaluation. Sparse autoencoders on randomly initialized transformers can receive similar automated interpretability scores to those on trained models. In a recent synthetic test with known features, strong reconstruction recovered only a small fraction of the ground truth, while constrained random baselines nearly matched trained autoencoders on interpretation, probing, and causal editing. Readability alone is not enough. The picture is not static. Subspace-aware and more flexible autoencoders are being developed to reduce splitting, and some 2026 results improve reconstruction and downstream behavior. But on the mechanistic interpretability benchmark, sparse features did not outperform ordinary neurons at causal variable localization, and DeepMind found linear probes stronger for one out-of-distribution safety task. The appropriate claim remains method and task-specific. Sparse features are best understood today as learned instruments, indexes, compressed descriptions, steering handles, and hypothesis generators. A clean label or successful edit does not prove that one latent is an elementary variable in the model's native computation. That stronger claim requires reproducibility, causal specificity, useful baselines, and evidence that downstream components actually operate on the proposed feature. Transcoders move from representing activations toward representing component functions. Instead of rebuilding a layer's input, they learn a sparse approximation of what a multilayer perceptron writes. Cross-layer transcoders may send one learned feature directly to several later layers, producing much shorter paths. This makes large causal graphs easier to inspect, but it also introduces an interpretable replacement for part of the original model. Anthropic circuit tracing system runs a prompt through this replacement model, identifies active sparse features, and traces strong contributions backward from the selected output. The resulting attribution graph can support concrete hypotheses about a single prediction, and targeted interventions can test selected paths against the original model. It is perhaps the most powerful exploratory interface the field has produced at frontier scale. The graph is nevertheless partial. Reconstruction error becomes dark matter nodes. Query key computations that create attention patterns are not fully explained. Inactive and inhibitory features are difficult to trace. Features may appear at the wrong abstraction level, and weak edges are pruned. Most importantly, the visible edges belong to the sparse replacement, so their connection to the dense model must be validated rather than assumed. A June 2026 result shows the danger directly in a Boolean model whose true circuit is known. A cross-layer transcoder replaced a deep sequence of dependent steps with several shallow shortcuts. It preserved the output behavior while hiding the actual route, and the sparsity objective preferred the rewrite. Preliminary language model experiments also produced conflicting circuit stories from different replacement models. Causal abstraction proposes a more explicit test. Start with a low-level neural network and a high-level algorithm. Choose a map between their internal states. Intervene on a neural state, translate the result upward, and compare it with the high-level system after the corresponding intervention. If many matched interventions produce the same downstream behavior, the algorithm is a causally faithful abstraction under that map. Dennis Sutter and colleagues reveal a decisive identification problem. If the mapping is allowed to be an arbitrarily powerful nonlinear translator, then under broad conditions, any network can be made to match any algorithm. They trained such a map from a randomly initialized language model to the indirect object algorithm and obtained perfect interchange intervention accuracy, even though the random model could not perform the task. The translator learned the explanation. Restricting the map to be simple avoids that construction, but now simplicity and linearity are assumptions that must be justified. This is the difference between validation and identification. Passing a chosen intervention test shows compatibility with one explanation. Identifying a mechanism requires tests that rule out rival variables, rival maps, rival circuits, and flexible translators that can manufacture agreement. The strongest recoveries still occur in controlled model organisms, small systems trained on modular arithmetic, formal languages, tree tasks, or satisfiability problems. There the input domain is bounded, candidate algorithms are precise, and researchers can test nearly all relevant computation. Recent formal work can even certify domain robustness, robust patching, and minimality in bounded settings, although current demonstrations remain limited and expensive. Another promising route changes training itself, using sparse weights or architectural constraints so simpler circuits are present by construction rather than extracted afterward. The honest state of mechanistic interpretability is neither triumph nor failure. We can observe routing, decode information, localize causal influence, recover narrow algorithms, build sparse interfaces, and generate testable hypotheses in large models. We cannot yet routinely recover stable, complete, human-comprehensible mechanisms for frontier model cognition. Stronger claims need justified variables, predicted interventions, robustness, competitive baselines, constrained maps, and explicit residual coverage. That conclusion points forward. Going causal is necessary, but a causal effect is not yet a causal mechanism. The remaining problem is causal identification, designing interventions that distinguish the organization used by the model from a story imposed by our tools. This is the shift NeuralCipher is built for. NeuralCipher. Deciphering learned computation.